Hi, my name is Shaira Iman binti Sirajuddin, and I'm a student from Bachelor of Aerospace Engineering, and I would like to present my final year project on finless airship dynamics modeling using Simulink. So first, I'm going to discuss about the problem statement. Modeling and simulation are vital in accelerating the studies of airships' flight dynamics and its control development. Second, running experimental testing for airship is very costly and time-consuming. Third, modeling of airship dynamics have lagged behind and are less systematic when we compare it with the aircraft. So in order to overcome those problems, the aims and objectives of these projects are to determine physical configuration and flight airship through experimental flight tests, specifically for PSR2, our very own finless airship in UVM, and second, to develop a dynamic model and 6 degrees of freedom nonlinear simulation model of finless airship. So, first of all, for the methodology, we need to acquire the PSR2 or the configuration and specification. Next, doing a literature review on existing airship nonlinear dynamics model, which are important in order to get the identification assumptions for the dynamic modeling later on. Third, the development of nonlinear dynamics model that consists of 4 models that are mass model, aerodynamic model, buoyancy model, and lastly the propulsive model. So we need to obtain the parameters of the airship model to experimental. So some of the parameters, such as the location of COB, center of buoyancy, and the location of CG, center of gravity, is needed in order to get the RZ. The vertical distance between these two, COB and CG. Moving on, completion of mathematical model of finless airship and development of Simulink model. Then we're going to analyze the airship model response to propulsive input, whether the response is appropriate to the propulsive input given. So the equations of motions actually are nonlinear and force-based model. M double dot X or MA equivalent to A plus J plus P, which are A the aerodynamic, G is the restoring forces, and P the propulsion forces. So we can see that from this diagram, the buoyancy model, thruster A, G, P, and M are needed in order to get the double dot X, the acceleration, and differentiate it, we're gonna get the velocity, UVW, PQR, and differentiate lastly, we're gonna get the position, which is X, Y, Z, theta, phi, psi, the airship dynamics that we need to observe. These are the mass model, and we can see that in order to complete this mass model, we need the location of COB, location of CG, as well as the RZ. So from the experiment, we can conclude that COB, location of COB and CG are actually aligned in horizontally, but there is a difference in vertical direction. Hence, there is RZ, the vertical distance between COB and CG, and the distance is 0.38 meter. And we have the aerodynamic force, the restoring force, and lastly the propulsion force, or the input, where the input actually shows that the motion of the airship for the dynamic modeling dependent on these two thruster configurations and servo angle configuration. So you can see from the search motion for the dynamic modeling, so motor 1 and motor 3 only needed for search motion, and it is angled at 90 degrees facing forward. And you can see that at velocity u, it moved forward, but it has pitch motion as well. This is due to the difference of COB and CG, the RZ, and it is called as pendulum stability in pitch motion. And you can see that it moved in X direction from 0 meter towards 40 meter. And the Asia velocity response can also be seen due to difference in RZ, where at 0.1 the pitch motion is very subtle, while in 0.5 the pitch motion is crowded, or I can say that there has a there are many pitch motion in this distance. And we have the heave motion, where all motors are needed and at the same thrust. You can see that the position of in Z direction, the airship actually moved from 0 meter towards 60 meters. So it moved upward. And for pitch motion, motor 1 and motor 3 are facing upward, while motor 4, motor 2 is facing downward. And from there, the proportion input, we can see that the attitude of it shows the attitude in pitch motion. It pitching from 20 degrees towards negative 20 degrees until the end of simulation. The pitching moment also is unstable due to the pendulum stability, the difference in COB and CG. And you can see the difference from 0 meter towards 0.5 meter. At 0 meter, the response of the pitch, it does not move when it from 0 degree, it moves towards 45 degree and it stays until the end of simulation at 45 degree. But for 0.5, from 0.1 towards 0.5, there is a difference in pitch motion, where it keeps pitching up, pitching down until the end of the simulation. And then we have the yaw motion, where the attitude yaw is also shown with the input from all the motors and the servo angle. And we have the pure roll motion as well, where it shows the attitude in roll motion. Like the pitch motion, the roll motion is also unstable, and it is unstable towards the end of simulation due to the pendulum stability, but in roll direction. And we have the mission profile for airship, where the airship climbs, and then cruise, descent, and lastly landing. So what I can conclude that this project actually able to determine the physical configuration, the RZ, the location of COB and location of CG, and lastly the dynamic model also is able to develop, and it shows appropriate response towards the propulsive input. And I think that is all from me. Thank you.